The chisel snapped clean in half. Not bent, not dulled, snapped as if it had struck stone instead of wood. Hauptmann Friedrich Müller stared at the broken tool in his palm, then back at the pale wooden panel lying on the workbench. Around him, in a converted warehouse outside Bremen, a team of Luftwaffe technicians stood frozen, watching their supervisor attempt something that should have been simple, separating two thin layers of British plywood. It was March 1943. The aircraft they were dissecting had been shot down 3 days earlier over the Frisian coast, a British bomber that had somehow limped 60 kilometers on a shattered engine before its pilot belly landed in a turnip field. When the recovery crew arrived, they expected the usual carnage of twisted metal and scorched aluminum. Instead, they found something that looked like it belonged in a cabinet maker's shop. "Try the hydraulic press," Müller said quietly, his voice betraying frustration. The machine groaned as pressure built. 500 kilograms. 800. At 1,200 kilograms, the wood fibers began to compress and splinter, but the adhesive line between them remained perfectly intact, a thin golden seam that refused to surrender. Someone in the back of the room laughed nervously. The English are gluing together furniture and calling it a bomber, but Müller wasn't laughing. He'd spent the last 2 years analyzing wreckage from downed aircraft, Spitfires, Hurricanes, even the occasional American Fortress. He knew structural failure when he saw it. And this wasn't failure. This was something his engineering textbooks had never predicted. The smell hit him again, that strange sweetness that clung to everything. Not the petroleum reek of aviation fuel, or the acrid burn of combat damage. Something else entirely. Something that reminded him of the chemistry laboratory where he'd studied before the war, before everything became about aluminum and steel, and how quickly you could turn raw materials into weapons. One of his assistants, a young engineer named Klaus, approached with a clipboard. "Herr Hauptmann, the weight calculations are complete." He paused as if afraid to continue. "The entire fuselage shell, both halves complete with all structural members, weighs less than a Volkswagen." Müller looked up sharply. "That's impossible. Check again." "We've checked 3 times, sir. The British have built a twin-engine bomber that weighs less than our single-engine fighters." Across the room, another technician called out, "You need to see this." He was holding a cross-section of the wing spar under a magnifying glass. The wood grain, it's been oriented at different angles in each layer, like fabric in a tire. Each sheet compensates for the weakness of the one below it. Müller walked over, adjusted the magnification, and felt something shift in his understanding of what he was looking at. This wasn't carpentry that had been adapted for aviation. This was engineering that had been disguised as woodworking. The British had played a trick on them, on all of them. While Germany poured its resources into steel mills and aluminum refineries, while they'd built an empire of precision metalwork, the enemy had quietly turned to their furniture makers and asked a question no one at the Luftwaffe had thought to ask. What if the future of aviation wasn't stronger metal but smarter wood? Outside, the sound of air raid sirens began to wail. Another daylight intrusion. Müller felt his jaw tighten. He knew what aircraft would likely be overhead. Fast, wooden, impossible to catch. The same design currently lying in pieces on his workbench. "Package everything," he ordered. "Berlin will want to see this, all of it." As his team began carefully wrapping fragments in cotton cloth, Müller placed his hand on the fuselage panel one more time. It was smooth, almost warm to the touch, and impossibly strong. Somewhere in Britain, in factories he'd probably never heard of, craftsmen were building dozens of these machines every month, building them with glue and wood and an audacity that now, standing in this warehouse with a broken chisel in his pocket, terrified him more than any metal bomber ever could. The question wasn't whether Germany could copy this design. The question was whether they understood what it represented, a completely different philosophy of war, where the most dangerous weapons weren't the ones that looked most fearsome, but the ones that refused to play by anyone else's rules. 1938, the ministry that laughed at wood. The conference room in Whitehall smelled of pipe tobacco and old carpet. 6 men from the Air Ministry sat around a mahogany table, reviewing procurement proposals with the enthusiasm of accountants auditing a failed business. Geoffrey de Havilland stood at the far end, one hand resting on a rolled blueprint, the other in his pocket. He'd been speaking for 11 minutes. In that time, he'd watched the expressions around the table shift from polite attention to poorly concealed amusement. "Let me understand this correctly," Air Vice Marshal Wilfred Freeman said, tapping his pencil against his notepad. "You're proposing we build a bomber, a frontline combat aircraft, out of wood?" "Not just wood," de Havilland replied evenly. "A laminated composite structure using—" "Wood," Freeman interrupted. "You're talking about wood, while Rolls-Royce is developing engines that produce over 1,000 horsepower, while we're investing in aluminum alloys that can withstand forces your timber could never endure." He paused. "Mr. de Havilland, we're preparing for a modern war, not building garden sheds." A few chuckles rippled around the table. De Havilland didn't flinch. He'd expected this. The British aircraft industry had spent 2 decades perfecting all-metal construction. The Spitfire, the Hurricane, these were monuments to aluminum and stressed skin engineering. His proposal seemed like a step backward, and he understood why. "Gentlemen," he said, unrolling the blueprint across the table, "humor me for a moment. What's the current bottleneck in fighter production?" "Aluminum sheet," answered Squadron Leader Ralph Sorley, the only man in the room who seemed genuinely interested. "We're importing it from Canada, competing with American orders. Every Spitfire we build requires approximately 2 tons of processed aluminum." "Exactly. And when war comes, not if, when, that supply will be threatened by U-boats. Meanwhile," de Havilland traced a finger along the blueprint's clean lines, "Britain has something Germany doesn't have nearly as much of: skilled woodworkers, furniture makers, piano builders, boat craftsmen, 20,000 small workshops that currently have no role in aircraft production." "Because we don't build wooden aircraft anymore," Freeman said flatly. "Because we've forgotten how powerful wood can be when properly engineered." De Havilland pulled out a small wooden sample from his briefcase, 3 thin layers bonded together, each barely 2 millimeters thick. He placed it on the table. "This is birch plywood bonded with synthetic resin under heat and pressure. It's lighter than aluminum, stronger per weight, and—" He picked it up and flexed it between his hands. "It absorbs stress differently. Where metal fatigues and cracks, this flexes and returns." "And when it's hit by cannon fire?" Freeman asked. "It doesn't shatter into shrapnel that can sever control cables and fuel lines. A hole in wood is just a hole. It doesn't propagate." The room fell silent for a moment. De Havilland pressed his advantage. "You're worried about performance, so am I. That's why this bomber will carry no defensive armament." "No guns?" Freeman's voice rose. "You want to send men over Germany in an unarmed wooden aircraft? I want to send them in an aircraft so fast that nothing can catch it. No turrets means less weight. Less weight means more speed. More speed means survival." De Havilland leaned forward. "Gentlemen, we're designing bombers as if they're medieval castles. Thick walls, defensive towers. But castles fell to cannons. What if instead we built something so quick, so agile, that it simply isn't there when the shells arrive?" Sorley was nodding slowly. "What kind of speed are you predicting?" 400 miles per hour, faster than the Spitfire." The room erupted in scoffs. "That's fantasy," Freeman said. "No bomber has ever—" "No metal bomber," de Havilland corrected. "But remove 2 tons of aluminum. Replace it with precisely engineered wood. Eliminate the gun turrets and their crews. Streamline everything. Yes, 400 miles per hour. Maybe more." Freeman stood, clearly ready to end the meeting. "Mr. de Havilland, I respect your company's work. The Tiger Moth is an excellent trainer. But this," he gestured at the blueprint, "is not a serious proposal for modern warfare. We need metal. We need armor. We need proven technology, not experimental furniture." De Havilland carefully rolled up his blueprint. He'd known this was a long shot. But before he left, he tried one more angle. "How much aluminum does Britain have stockpiled right now?" Freeman frowned. "That's classified. Then I'll tell you what your own ministry reports say. Enough for approximately 9 months of peak production, assuming no supply disruptions. U-boats are already being built in German shipyards. When they cut the Atlantic supply lines, and they will, every pound of aluminum will become a strategic crisis. He tucked the blueprint under his arm. I'm offering you an aircraft that doesn't compete for strategic materials. One that can be built in workshops across the country, using skills and materials we have in abundance. You're calling it a garden shed. I'm calling it insurance. He walked to the door, then turned back. War has a way of making the impossible suddenly practical. I'll keep this design ready. When you need it, and you will, it'll be waiting. The door closed softly behind him. In the quiet that followed, Sorley picked up the wooden sample de Havilland had left behind. He flexed it between his fingers, watching how it bent without splitting. He might be insane, Sorley said quietly. Freeman was lighting his pipe. Completely. But what if he's right? Freeman didn't answer. Outside, the rumble of London traffic mixed with the distant sound of construction, new factories going up, metal foundries expanding. The machinery of war was already beginning to turn, and everyone knew it. The only question was whether Britain would have enough metal to build what it needed. That wooden sample stayed on Sorley's desk for the next 8 months. He'd pick it up occasionally during long meetings, flexing it absent-mindedly, while discussing production quotas and material shortages. When France fell in June 1940, and the aluminum supply line suddenly became far more precious than gold, he remembered de Havilland's words, insurance. The call went out on July 12, 1940. The Air Ministry wanted to see those blueprints again. The factory that shouldn't have worked. The building had been producing mahogany dining tables the week before. Now, in October 1940, it was building bombers. Sarah Mitchell adjusted her safety goggles and ran her hand along the curved wooden mold, checking for imperfections. Around her, in what had once been a furniture showroom in Leavesden, 50 other workers, most of them women, most of them former upholsterers, carpenters' assistants, and piano finishers, were transforming sheets of thin wood into something the RAF had declared impossible. "How's the cure looking?" asked Tom Whitmore, the floor supervisor. He'd been building cabinets for luxury hotels before the war. Now he was overseeing the construction of aircraft wings. "Another 20 minutes at temperature," Sarah replied, checking the thermometer embedded in the mold. "The resin needs to hit exactly 110 degrees. Hold it there, then cool slowly. If we rush it, it delaminates, I remember." Tom made a note on his clipboard. "We lost 2 fuselage halves last week because someone opened the press too early. The Air Ministry inspector nearly had an apoplexy." Sarah smiled. The inspectors, all of them trained in metal aircraft construction, had arrived at the factory expecting to find chaos. Instead, they'd found precision that rivaled any aluminum workshop, just executed with completely different tools. Where metal workers used riveting guns and welding torches, the Mosquito workers used glue brushes, heating elements, and wooden forms that had been carved with the kind of accuracy usually reserved for fine musical instruments. The process seemed simple on paper. Take thin sheets of birch plywood, spread a layer of phenol formaldehyde resin between them, add a core of lightweight balsa wood from Ecuador, then laminate it all together under heat and pressure. In practice, it required an almost musical sense of timing. "Temperature's perfect," Sarah called out, "releasing pressure now." The hydraulic press hissed as it opened. Steam, moisture driven out of the wood by the curing process, rose like morning mist. As it cleared, Sarah saw what they'd created. A curved fuselage section, smooth as glass, strong as steel, and light enough that she could lift it with one hand. Tom ran his fingers along the edge. "Beautiful work. That's the port side for aircraft W4072. Starboard half should be ready in about..." He checked his watch. 40 minutes. If the glue gods are kind. "The glue gods," Sarah repeated with a laugh. It had become a running joke in the factory. So much of the Mosquito's strength depended on that adhesive, a synthetic resin that bonded wood fibers at the molecular level. Get the mixture wrong, Apply too much or too little heat, rush the curing time, and the entire structure would fail. Get it right, and you created something stronger than riveted aluminum. Across the factory floor, other stations were building different components. At Station 3, former boat builders were shaping the one-piece wing sections, massive wooden structures that would be assembled without a single metal fastener. At Station 7, craftsmen who'd once built Steinway pianos were hand-fitting the curved nose cone, using skills that had taken years to master for an entirely new purpose. An RAF officer appeared at Sarah's elbow, Squadron Leader Davies, one of the liaisons between the factory and the military. He'd been skeptical when first assigned here, had made jokes about flying plywood. 3 months later, his attitude had completely changed. "How many complete aircraft this week?" he asked Tom. 11 fuselages ready for final assembly, 9 wing sets completed. Should have 14 complete airframes ready for engine installation by Friday. Davies whistled softly. 14. The metal factories are managing 8 Lancasters a week, and they're using 5 times the workforce. Furniture makers work fast when properly motivated, Tom said. Plus, we don't need to wait for rivets, sheet aluminum, or specialized metalworking equipment. Wood arrives by the truckload, we cut it, glue it, press it, and it's done. And the workers? Davies asked, glancing around the factory floor. Any quality issues? Tom shook his head. These people have been working with wood their entire lives. They can feel when something's wrong. A bad grain pattern, uneven curing, a weak glue line. That kind of tactile knowledge takes decades to develop. You can't train it, you have to have lived it. Sarah was already moving to her next task, inspecting a completed fuselage half for defects. She'd learned to read wood the way a mechanic reads metal, looking for stress lines, weak points, areas where the structure might fail under combat conditions. She ran her hand along the inside surface, feeling for irregularities. Perfectly smooth. The lamination process had turned dozens of thin sheets into a single unified shell. She knocked her knuckles against it experimentally. The sound was resonant, almost musical. Solid. "This one's good," she called out. "Ready for mating." 2 workers wheeled over the starboard fuselage half. This was the critical moment, when the 2 mirror image sections would be bonded together to create the complete fuselage. The process required perfect alignment, even adhesive application, and patience. They positioned the halves in a specially designed jig, spread a carefully measured layer of resin along the joining edges, then slowly brought them together. Clamps tightened gradually, ensuring even pressure. Within the sealed joint, the resin would cure into an airtight bond stronger than any welded seam. 12 hours in the jig, Tom said, making notes. Then it goes to final finish. Davies was shaking his head in wonder. "I watched a Lancaster being built last month. Took 4,000 man-hours just for the basic airframe. How long for a Mosquito? Complete airframe, ready for engines and systems? About 3,000 hours. But," Tom gestured around the factory, "we can run multiple production lines simultaneously. These methods scale beautifully. You can't easily scale up a metal fabrication shop, but you can teach woodworking to anyone with patience and decent hands." As they spoke, Sarah noticed something that always struck her. The smell. Metal factories reeked of cutting oil, hot metal, and ozone from welding arcs. This factory smelled like a cabinet maker's workshop, sawdust, resin, and the sweet chemical scent of curing adhesive. It felt wrong that such a domestic smell could be associated with weapons of war. But that was the Mosquito's secret, wasn't it? It refused to look, sound, or smell like a weapon. It looked like fine furniture, it smelled like a carpenter's shop, and somehow that made it deadlier. By the end of the shift, Sarah had inspected 7 fuselage sections, all perfect. As she clocked out and walked into the October evening, she passed the final assembly hangar where completed Mosquitoes, painted camouflage green and gray, waited for test flights. One of the test pilots, a squadron leader named Martin, was doing a walk-around inspection. He saw Sarah and waved. "You worked on W4068?" he called. "That's mine," Sarah confirmed. "Something wrong." "Wrong. I took her up this afternoon," Hit 403 miles per hour in level flight. That's faster than anything Germany has. He patted the wooden fuselage affectionately. You furniture people are winning this war? Sarah felt a swell of pride, then immediately felt guilty for it. This beautiful machine she'd helped build would fly into danger. Might be shot down, might kill people. The moral weight of it was complicated. But watching it sit there under the floodlights, sleek, purposeful, impossibly fast, she understood what de Havilland had seen. This wasn't just an aircraft. It was proof that elegance and lethality weren't opposites, that the future sometimes looked like the past, that wood and glue in the right hands could defeat steel and fire. As she walked home through the blackout, she heard the distant rumble of bombers overhead, the heavy metal ones flying to Germany with their loads of destruction, and she knew that soon, mixed in among them, would be the wooden ones, the ones she'd helped build, flying faster, flying higher, and returning home when others didn't. The furniture factory had become a weapons plant, and somehow, impossibly, it was working. The pilot who trusted would flight Lieutenant Robert Bobby. Clark pressed his palms against the fuselage and felt it flex slightly. Not a failure, just movement, like a living thing breathing. It unnerved him. You're sure this thing won't just fall apart? He asked the ground engineer, trying to keep his voice light. Wood's been holding up ships for thousands of years, sir, the engineer replied cheerfully. I reckon it'll manage one little bomber. Bobby climbed up the access ladder and lowered himself into the cockpit. Beside him, his navigator, Flight Sergeant Thomas Price, was already settling in, checking maps and instruments. The cockpit was cramped, just barely enough room for two men shoulder to shoulder. No gun turret behind them, no tail gunner. If they got into trouble, their only defense was the throttle. This was Bobby's third operational flight in a Mosquito. The first had been a milk run to photograph French coastal defenses. The second, a bombing raid on rail yards in Belgium. Both times he'd returned feeling like he'd cheated death through a technicality. The enemy simply couldn't catch him. But today was different. Today they were going to Berlin. Navigator ready? Bobby asked. Ready as I'll ever be for this mad idea, Tom replied. Broad daylight, straight to the capital, and we're making tea time appointments with Göring. Bobby adjusted his harness and scanned the instruments. Everything looked good. The twin Rolls-Royce Merlin engines, the same power plants that drove Spitfires, were purring smoothly. The difference was the Spitfire was a fighter carrying guns and armor. The Mosquito was a bomber carrying speed and hope. Tower, this is Mosquito Sugar Victor. Request clearance for takeoff. Roger, Sugar Victor. Wind is 270 at 15 knots. You're cleared for immediate departure. Give 'em hell. Bobby advanced the throttles. The Merlins roared, that distinctive sound that meant power and British engineering and survival. The wooden bomber began rolling, picking up speed faster than anything its size had a right to. At 95 miles per hour, Bobby pulled back gently. The Mosquito leapt off the runway like it had been waiting its whole life for this moment. Climb rate, 2,850 feet per minute. He glanced at Tom, who was grinning despite himself. She wants to fly, Tom said. She wants to live, Bobby corrected. They climbed through patchy cloud cover, heading east toward a country that wanted them dead. The briefing had been characteristically insane. Fly at 25,000 feet, approaching Berlin from the north. Drop 4 500-pound bombs on the Air Ministry headquarters. Then run for home faster than anything could follow. At altitude, the world became silent except for the steady drone of engines. No defensive gunfire to worry about. Yet. No flak. Yet. Just empty sky and the knowledge that somewhere below, radar stations were tracking them, fighter controllers were scrambling interceptors, and German pilots were climbing hard to meet them. 15 minutes to target, Tom announced, his voice steady despite the circumstances. Bobby scanned the horizon. Nothing yet. The Mosquito felt alive beneath him, not like metal which was inert and dead, but like wood, which had been a tree once, which still flexed and breathed and responded to stress with resilience rather than brittleness. A thought occurred to him. German fighters were all metal, rigid, strong, but inflexible. If a Focke-Wulf took structural damage, the metal tore and failed catastrophically. But wood. Wood could be riddled with bullets and still hold together, the fibers gripping each other, the glue maintaining integrity even when the surrounding structure was compromised. It was almost poetic, if you ignored the part where you might die. "Fighters, 3 o'clock low," Tom suddenly called. Bobby saw them, 2 Messerschmitt Bf-109s climbing hard, still 2,000 feet below. They'd spotted the Mosquito and were trying to intercept. "Can they reach us?" Bobby asked, though he already knew the answer. "Not at this speed. We're pulling away." And they were. Even with the German fighters at full throttle, straining to close the gap, the Mosquito simply accelerated beyond their reach. Bobby watched them fall behind, shrinking into the distance, and felt a strange mixture of relief and pity. Those pilots were brave men doing their jobs. They just had the wrong airplane. "Target visual," Tom said. 2 minutes. Berlin spread out below them, a vast city that thought itself untouchable. For 2 years it had been bombed only at night, by slow, heavy bombers that crept in under cover of darkness. Nobody had dared attack in daylight. Until now. "Bomb bay doors open," Bobby confirmed. The aircraft shuddered slightly as the doors swung down into the slipstream. He could feel the increased drag, but it barely mattered. They were still doing 380 miles per hour at altitude. 5, 4, 3, 2, 1. Bombs away. The Mosquito lurched upward as 2 tons of explosives fell away. Bobby immediately put the aircraft into a shallow dive, building speed, turning northwest toward home. Below, sirens were wailing. German citizens were running for shelters. And somewhere in an underground bunker, Hermann Göring was about to learn that British bombers, wooden bombers, furniture factory bombers, had just struck his headquarters in the middle of the day. The return flight was a blur of adrenaline and disbelief. More fighters tried to intercept them over Holland. All failed. By the time Bobby crossed the English coast, he was laughing, not from joy, but from the sheer absurdity of it. They'd flown to Berlin and back in a wooden airplane, and the entire German air defense system couldn't stop them. Landing was smooth. As Bobby taxied to the dispersal area, he saw the ground crews staring at them with something like awe. They knew where Sugar Victor had been. They knew what she'd done. Bobby shut down the engines and sat in silence for a moment. His hands were shaking. Delayed reaction, he told himself. Tom was already climbing out, talking excitedly to the waiting intelligence officer. Bobby placed his palm against the wooden instrument panel one more time. Warm from the sun, smooth from the finish, and absolutely, impossibly alive. "Thank you," he whispered to the aircraft. Then he climbed out to file his mission report and try to explain how a bomber made of furniture had just humiliated the Third Reich. The chemist's nightmare. Dr. Werner Schultz stood in his laboratory at the Kaiser Wilhelm Institute, staring at the chemical formula on the blackboard as if it were a personal insult. Around him, beakers bubbled over Bunsen burners, and the air smelled of phenol and formaldehyde. Industrial chemicals that Germany produced in vast quantities, but had never thought to combine in quite this way. The sample on his desk, a small fragment of British wood composite, carefully extracted from the captured Mosquito, mocked him with its simplicity. 3 layers of birch plywood bonded with a resin that his preliminary analysis had identified as phenol formaldehyde, heated and cross-linked into a thermoset polymer. It wasn't exotic, it wasn't even particularly complex, and that was what made it so infuriating. "We've been making phenolic resins since 1907, he muttered to his assistant Hans. "Bakelite, electrical insulators, radio casings. Why didn't we think of using it in aircraft?" Hans, a younger chemist who'd specialized in polymer science before the war, looked up from his microscope. "Because we were solving different problems, Herr Doctor. We were trying to make aluminum alloys lighter and stronger. The British were trying to make wood perform like metal." Schultz picked up the sample again, bending it between his fingers. Even this small piece, barely 5 centimeters square, demonstrated remarkable properties. The resin had penetrated deep into the wood grain, creating a molecular bond that turned the organic fibers into something closer to reinforced plastic. "Run the heat tolerance test again," Schultz ordered. I want to know exactly how stable this adhesive is under combat conditions. Hans nodded and carefully placed a fresh sample into a furnace. They'd been testing British adhesive properties for 3 weeks now, and each experiment revealed new surprises. The resin didn't just glue wood together, it fundamentally altered the wood's properties, making it more heat-resistant, more moisture-resistant, and far stronger than untreated timber. The temperature gauge climbed, 80 degrees Celsius, 100, 120. At 150 degrees, far hotter than any aircraft structure would normally experience, the wood began to char, but the glue lines remained intact. Extraordinary, Hans whispered. Even at temperatures that would cause aluminum to lose structural integrity, the composite maintains cohesion. Schultz made notes, his handwriting growing more agitated. The implications were becoming clear, and they weren't pleasant. Germany had the chemistry. They had the industrial capacity. What they didn't have was the imagination to see wood as a strategic material. A knock at the laboratory door interrupted his thoughts. A Luftwaffe officer entered, carrying a leather briefcase. "Dr. Schultz, I'm Oberstleutnant Brenner from the Air Ministry. I understand you've been analyzing the British adhesive system." "I have," Schultz confirmed. "Your report requested a full chemical breakdown and an assessment of whether we can replicate it." "And can we?" Schultz gestured to the blackboard covered in formulas. "Technically, yes. The chemistry is straightforward. Phenol and formaldehyde, combined in approximately a 1 to 1.5 molar ratio. With a basic catalyst, heated under pressure. It forms a thermoset resin with exceptional bonding properties. Then we can build our own wooden bombers?" Brenner looked hopeful. "I didn't say that." Schultz picked up another sample, this one from a German training glider that used Chisel adhesive. "Look at this. This is what we currently use for wooden aircraft components. Casein, milk protein mixed with lime. It works adequately in dry conditions, but..." He placed it in a beaker of water. Within seconds, the glue line began to soften and swell. Moisture is its enemy. The British resin, by contrast, he placed a British sample in an identical beaker, is completely impervious. They watched for several minutes. The German sample gradually delaminated, layers separating like pages in a wet book. The British sample remained perfectly bonded. "The problem," Schultz continued, "isn't that we can't make phenolic resin. We can. The problem is that we're already using all available phenol for other purposes." "What purposes?" Brenner demanded. "Explosives, specifically picric acid production for artillery shells. Every gram of phenol we divert to aircraft adhesive is a gram we can't use for ammunition." Schultz retrieved a production report from his desk. "Current German phenol production, approximately 15,000 tons per year. Current demand, 22,000 tons. We're already running a deficit." Brenner's face darkened. "So we'd need to choose between bombs and bombers. Not just bombs, also synthetic rubber, pharmaceuticals, disinfectants for field hospitals. Phenol is one of the most strategically important chemicals we produce, and we're already stretched thin." Schultz sat down heavily. "The British had a different equation. They had abundant wood and limited aluminum. We have abundant aluminum and limited chemical precursors. They optimized for their constraints. We optimized for ours. But surely if the Führer ordered, if we received direct orders, we could divert production. But it would mean sacrificing something else." Schultz pulled out a calculator and began working through numbers. "To produce enough phenolic resin for, say, 100 wooden bombers per month, we'd need approximately 200 tons of phenol. That's enough to produce 450 tons of TNT, or 800,000 artillery shells, or medical supplies for 30 field hospitals." The room fell silent except for the bubbling of the beakers. Brenner finally spoke, his voice quiet. "So, the British beat us not with superior chemistry, but with superior strategy. They built an adhesive-intensive aircraft because adhesives were something they had in abundance." "Exactly. And they designed the entire aircraft around that constraint. No rivets means no aluminum. No aluminum means more weight savings. More weight savings means higher speed. It's a cascade of intelligent compromises, each one leveraging their advantages. Hans spoke up from his workstation. There's another factor, Herr Doctor, the curing process. The British resin requires precise temperature control, exactly 110 to 120 degrees Celsius, maintained for several hours. That requires specialized equipment, reliable electricity, and trained operators. 1943, with Allied bombing disrupting our power grid and our factories. He didn't need to finish the sentence. Schultz stood and walked to the window, looking out over Berlin's rooftops. Somewhere up there, British mosquitoes flew with impunity, each one held together by the very adhesive he'd been studying, each one a testament to what happened when engineering met imagination. "Write this in your report to the Air Ministry," Schultz said to Brenner. "The British adhesive system is not a secret weapon. It's a public humiliation. They've demonstrated that with commonly available chemicals and furniture factory techniques, they can build bombers that outperform our finest metal engineering. We could replicate their adhesive. We could even improve upon it. But we cannot replicate the circumstances that made it necessary, the scarcity that forced innovation." Brenner gathered his papers, looking defeated. "So your recommendation is? Focus on what we do well. Metal aircraft, where we have both materials and expertise. Let the British have their wooden wonder. We'll never build it as well as they do because we don't need to." Schultz turned back to face him. "But make sure every engineer at the Luftwaffe understands what we learned here. The enemy's genius wasn't in inventing new chemistry. It was in asking a different question." After Brenner left, Schultz returned to his desk and picked up the British sample one more time. Such a simple thing, wood and glue. His daughter's school desk was probably held together with something not so different. Yet in the right hands, applied with the right vision, it had become a weapon that terrified the Third Reich. He placed it carefully in a specimen box, labeled it, and filed it away. Someday, when this war was over, chemists would study this adhesive not for its military applications, but for what it represented. Proof that innovation isn't about having the most resources, but about using the right resources in the right way. For now, though, it was just another reminder that Germany was losing the innovation war, one chemical formula at a time. When pride met physics. The test facility at Rechlin was Germany's finest, a sprawling complex of wind tunnels, engine test stands, and prototype hangars where the Luftwaffe's future was supposed to take shape. On a cold morning in November 1943, that future was about to crash into a marsh at 180 miles per hour. Flugkapitän Ernst Bauer stood beside the Focke-Wulf FU 195-37, watching technicians make final adjustments to a prototype that was supposed to prove German engineering could match anything the British built. The aircraft looked aggressive, all metal, painted in mottled camouflage, bristling with cannons and rockets. "Final weight check is complete," announced Oberingenieur Dietrich, reading from his clipboard. "Fully loaded, 4,190 kilograms. That's 340 kilograms over the design specification." Bauer frowned. "And the estimated top speed? Computer calculations suggest 385 miles per hour at optimal altitude. The Mosquito does 400. The Mosquito," Dietrich said with barely concealed frustration, "is made of wood and carries no defensive armament. This is a proper fighter bomber. Armor plating, guns, rockets. The weight is justified." Bauer said nothing. He'd flown combat missions over France and the Low Countries. He'd watched mosquitoes appear and disappear like ghosts, untouchable, mocking every attempt to intercept them. The weight might be justified on paper, but physics didn't care about justifications. "Let's get it airborne," he said finally. "Let's see what this proper fighter bomber can actually do." The FW-190 was a magnificent machine, powerful, well-built, a testament to German precision. But as the heavy canopy closed over him, he couldn't shake the feeling that they were fighting the wrong battle. The British had asked, "How fast can we make it?" The Germans had asked, "How much can we arm it?" Different questions led to different aircraft. The takeoff was smooth, the BMW radial engine roaring with authority. Bauer climbed to 20,000 feet and began the speed trials. At full throttle, the FW-190 V-37 accelerated impressively to 382 miles per hour. Then the airspeed needle stopped climbing. He pushed the throttle forward as far as it would go. Nothing. The aircraft had reached its absolute limit, held back by drag from the gun blisters, weight from the armor plating, and the fundamental reality that metal was heavy. 18 miles per hour slower than the Mosquito. In combat, that gap might as well be infinite. Bauer radioed down his findings, trying to keep the disappointment from his voice. On the ground, Dietrich would be making excuses about test conditions and environmental factors, but they both knew the truth. Rechlin control. Beginning descent, Bauer reported. Roger, proceed to... The radio operator's voice suddenly changed. Wait, we have an unidentified contact, bearing 270, altitude 24,000 feet, closing fast. Bauer craned his neck, scanning the sky. There. A small silhouette, distinctly twin-engine, moving with casual contempt through German airspace. A Mosquito, probably on a photo reconnaissance mission, taking pictures of this very facility. I see it, Bauer said. Request permission to intercept. Permission granted. Engage at will. This was it. A chance to prove that German steel could catch British plywood. Bauer banked hard, turning toward the enemy bomber, and pushed the throttle to maximum military power. The BMW engine screamed in protest, but the FW-190 responded, climbing and accelerating. The Mosquito was perhaps 3 miles away, 2 miles. Bauer could see it clearly now, sleek, impossibly elegant, reflecting afternoon sunlight off its varnished wooden skin. 1 mile. He armed his cannons. The gun sight locked on target. Just a few seconds more and he'd have firing range. Then the Mosquito pilot noticed him. The British aircraft didn't panic, didn't dive, didn't turn. It simply accelerated. Smoothly, almost lazily, it pulled away as if the FW-190 were standing still. Bauer held the throttle wide open, but it made no difference. The gap widened. 2 miles, 3 miles. Within a minute, the Mosquito had vanished into a cloud bank, leaving Bauer alone with his humiliation and his heavy, well-armed, inadequate fighter. Rechlin control, he said quietly. Target has evaded, returning to base. The landing was textbook perfect, but it felt like defeat. As Bauer climbed out of the cockpit, Dietrich was waiting with more bad news. We've received another report. The wooden bomber project. The Focke-Wulf Ta 154, the one that was supposed to be our answer to the Mosquito, has been cancelled. Why? Adhesive failure. The test aircraft broke apart during a high-speed dive. The glue couldn't handle the stress. Dietrich shook his head. We tried to copy their design using casein adhesive because we don't have enough phenolic resin. The substitute wasn't good enough. The entire program is being shut down. Bauer felt something heavy settle in his chest. It wasn't just one aircraft or one project. It was the realization that Germany was fighting a losing battle against an enemy that understood something fundamental. In war, the winner isn't the one with the most armor or the biggest guns. It's the one who solves the right problem. How many wooden bombers did we complete? Bauer asked. 18 prototypes, maybe 24 pre-production aircraft. None will see combat. Dietrich lit a cigarette with shaking hands. Meanwhile, British factories are producing 50 Mosquitoes per month, in furniture workshops, using craftsmen who couldn't tell an aileron from an elevator 6 months ago. They stood in silence, watching technicians service the FW-190, a beautiful, complex, expensive aircraft that couldn't catch the enemy. Want to know the worst part? Dietrich said. I spoke with one of the engineers who examined the captured Mosquito. He told me the British designed the entire aircraft to be repaired in the field. Damaged wood sections can be cut out and replaced with simple tools. Our metal aircraft need specialized welding equipment, replacement parts from factories, trained technicians. A Mosquito can be patched up with wood glue and canvas and fly again the next day. They outthought us, Bauer said simply. They outthought everyone. The Americans, the Russians, us. They looked at the problem differently. Dietrich crushed out his cigarette. We asked how to make our aircraft tougher. They asked how to make their aircraft not get hit in the first place. As the sun set over Rechlin, Bauer watched another formation of German fighters take off for combat patrol. Heavy, formidable, and ultimately ineffective against an enemy that refused to fight on German terms. Somewhere over the North Sea, Mosquitoes were already heading home from their daily missions, their wooden airframes absorbing the stress of high-speed flight, their furniture factory construction methods allowing for rapid replacement of battle damage, their complete absence of defensive armament paradoxically making them the most survivable bombers in the war. Pride had met physics, and physics had won. Germany could build magnificent aircraft. Britain had built the right aircraft. The difference, as Bauer was learning, was everything. The raids that changed everything. January 30th, 1943. 11 a.m. Berlin. Hermann Göring stood at the podium in the Berlin Sportpalast, preparing to deliver a radio address to the German people. Around him, Nazi officials sat in careful rows, their faces arranged in expressions of determination. The message was supposed to be about resolve, about Germany's inevitable victory, about the Luftwaffe's continued dominance of European skies. In the radio control booth, technicians adjusted microphones and checked signal strength. In 2 minutes, Göring's voice would reach every German household, every occupied territory, every front-line trench. The Reich's propaganda machine had arranged everything perfectly. At 11:02 a.m., as Göring opened his mouth to speak, the air raid sirens began to wail. The timing was too perfect to be coincidence. 2 Mosquito bombers, just 2, had appeared over Berlin at exactly the moment Göring began his speech. They flew at 25,000 feet, untouchable, and dropped their bombs with casual precision on the city's administrative district. The explosions rattled the Sportpalast's windows. Göring stopped mid-word, his face turning purple with rage. The radio broadcast carried the sound of distant detonations, followed by an awkward silence. Then the hasty announcer's voice. We are experiencing temporary technical difficulties. In Britain, intelligence officers listening to the broadcast heard everything. They smiled. Flight Lieutenant Jack Thompson was 24 years old and had flown 32 combat missions, which made him practically ancient by Mosquito Squadron standards. He sat in the dispersal hut at RAF Marham, reading a week-old newspaper and drinking tea that tasted like boiled socks. Thompson, the squadron commander, Wing Commander Perry, stuck his head through the doorway. Briefing in 10 minutes. Something special. 10 minutes later, Thompson and 11 other crews gathered around a map table. Perry pulled back the cover sheet, revealing a target that made everyone go quiet. Gentlemen, this is the Gestapo headquarters in Copenhagen. 3 buildings in the center of the city, holding approximately 150 Danish resistance prisoners. Intelligence suggests they're scheduled for execution within the week. Our job is to destroy the buildings and, with luck, allow some prisoners to escape in the chaos. Someone whistled low. That's a precision job, sir. Low-level daylight? Very low level. Rooftop height. You'll approach from the sea, navigate through Copenhagen streets, strike the targets with delayed action bombs, and egress at maximum speed before the Germans know what hit them. Perry looked around the room. I won't pretend this is safe. You'll be flying between buildings, dodging radio towers with minimal room for error. But if we don't do it, 150 people will die in those cellars. Thompson studied the map. The flight path showed a route threading through city streets like a needle through fabric. One wrong turn, one moment of hesitation, and you'd fly straight into an office building. Wooden aircraft, someone murmured. Flying through a city. The Germans will think we've gone mad. Let them think that, Perry said. We've proven the Mosquito can outrun anything they have. Now we're going to prove it can outthink them too. The mission launched 3 days later, on January 31st. 12 Mosquitoes formed up over the North Sea and flew east at wave-top height, using the curve of the Earth to hide from German radar. Denmark's coast appeared through morning mist, flat farmland, church steeples, and in the distance the spires of Copenhagen. Thompson flew in the second element, his navigator calling out checkpoints. The formation dropped even lower, barely 50 feet above the ground, and accelerated to 320 miles per hour. At that altitude and speed, the landscape became a blur. One mistake, one mechanical failure, and there would be no time to recover. 2 minutes to target, his navigator announced. Copenhagen's outskirts rushed past, houses, streets, people who looked up in shock at the wooden bombers screaming overhead. Then the city center rose ahead, all stone buildings and narrow alleys. IP in 5, 4, 3, 2, 1, mark, turn left 30 degrees. Thompson banked between buildings, his wingtip barely clearing a church tower. The Gestapo headquarters appeared ahead, a massive stone building with a courtyard. He could see people in the windows, frozen in disbelief as British bombers flew toward them at street level. Steady, steady, bombs away. The 500-pound bombs tumbled free with delayed fuses, 4 seconds to allow the Mosquitoes to clear the blast radius. Thompson pulled up hard, climbing over the building's roof with feet to spare, then dropped back down to rooftop level and turned for home. Behind him, the bombs detonated. The Gestapo headquarters erupted in flame and collapsing masonry. In the chaos, resistance prisoners in the basement cells would find their guards dead or fled. Doors blown open. A chance to escape. The return flight was a blur. Thompson's hands shook on the controls. Adrenaline and disbelief that he'd just flown through a city at 300 miles per hour in a wooden airplane. They landed at Marham 2 hours later. All 12 aircraft returned. No losses. Intelligence reports later confirmed that 26 resistance prisoners had escaped in the confusion. The Gestapo's Danish operations had been crippled, and German commanders in Copenhagen had learned what their counterparts in Berlin, Hamburg, and Oslo already knew. There was nowhere the Mosquito couldn't reach. The raids continued, each one more audacious than the last. On February 6th, Mosquitoes struck the Burmeister and Wain factory in Copenhagen, destroying German U-boat engines. On March 30th, they hit the Nazi Party headquarters in The Hague, with such precision that the building's facade collapsed, while surrounding Dutch buildings remained untouched. The Germans called it terror bombing, but they were wrong. It was surgical violence, proving that bombers didn't need to carpet bomb cities. With enough speed and precision, 2 aircraft could achieve what 50 heavy bombers struggled to accomplish. By mid-1943, the Mosquito had become psychological warfare. German commanders never knew when or where it would appear. The wooden ghost flew in daylight, at night, alone or in small formations. It photographed secret installations, dropped bombs on headquarters buildings, and vanished before interceptors could respond. Luftwaffe pilots began refusing to chase Mosquito contacts. "Why waste fuel?" they'd ask. "We'll never catch them." Ground controllers stopped scrambling fighters for single aircraft detections. Probably another Mosquito. Let it go. This was the ultimate success. An enemy so demoralized that they stopped trying to fight back. And all of it achieved by furniture makers, violin craftsmen, and piano builders, working in converted factories with wood and glue. The museum that remembers the Royal Air Force Museum at Hendon sits on the northern edge of London, housed in hangars that once sheltered fighters during the Blitz. Inside, among Spitfires and Hurricanes and Lancasters, there's a Mosquito. It's not the most impressive aircraft in the collection, smaller than the bombers, less glamorous than the fighters. But visitors always stop in front of it, drawn by something that transcends mere history. The placard reads, De Havilland Mosquito B Mank 16, wooden construction, maximum speed, 408 mph. Combat missions, 197, aircraft lost in combat, 0. That last number tells the entire story. 0 losses. This particular aircraft flew almost 200 missions into enemy territory and came home every single time, held together by wood and glue and the absolute certainty of its design philosophy. An elderly man stands before it now, his hand resting on the velvet rope that keeps visitors from touching the fuselage. His name is Robert Clark, though everyone calls him Bobby, and he's 91 years old. He flew Mosquitoes during the war, including the Berlin raids that made Göring scream with fury. A young boy, maybe 10 years old, approaches with his father. "Is it really made of wood?" the boy asks. Bobby smiles. "Every bit. Birch plywood and balsa, glued together in furniture factories by people who'd been making dining tables and pianos the year before. But wood isn't strong," the boy protests. "Neither is metal, if you ask the wrong questions about it." Bobby gestures to the Mosquito's smooth lines. The men who built this understood something important. Strength isn't about being hard. It's about being smart. Metal is hard, so it cracks. Wood is flexible, so it bends and returns. When I got hit by flak over Hamburg, it punched holes straight through both wings. A metal aircraft would have torn apart. This one, he pats the fuselage gently. This one just absorbed it and kept flying. The father looks skeptical. "Surely modern aircraft are better, with aluminum and composite materials?" "Modern aircraft use composite materials," Bobby corrects. "Carbon fiber, fiberglass, advanced resins. And where do you think that technology came from? Right here. From furniture makers who learned that if you layer materials correctly and bond them with the right adhesive, you can create something stronger and lighter than traditional construction methods." He runs his hand along the wing's leading edge. Still smooth after 80 years. The varnish yellowed but intact. "I flew this exact aircraft," Bobby says quietly. W4072. She carried me to Berlin and back 9 times. To Hamburg, Copenhagen, Oslo, Munich, places where I shouldn't have survived. But every time she brought me home. His voice catches slightly. "All my friends who flew heavy bombers, so many of them didn't come back. The metal fortresses with their armor and guns, they were supposed to be safer. But we furniture makers in our wooden bombers, we had the highest survival rate of any bomber command squadron." The boy is staring at the aircraft with new respect. "It doesn't look scary." "No," Bobby agrees. "It looks elegant, beautiful even. And that's the lesson the Germans never learned. The most dangerous weapons don't announce themselves. They don't need to look intimidating. They just need to work." As Bobby turns to leave, he places his hand on the fuselage one last time. Through the varnish and the decades, he swears he can still smell it, that distinctive sweet chemical scent of phenolic resin, the smell that meant safety and speed and survival. In the museum gift shop, you can buy postcards of the Mosquito. The description on the back is admirably brief, the wooden bomber that terrorized the Third Reich and changed aviation forever. But that's not quite right. The Mosquito didn't change aviation through terror. It changed aviation by proving that the most advanced solution to a problem isn't always the most complex. Sometimes it's the most elegant. Epilogue. What the glue taught us. In a laboratory at MIT in 1965, aerospace engineering students gathered around a sample of laminated wood composite, studying its properties as part of a course on aircraft materials. The professor held up the British wartime adhesive sample and explained how phenol formaldehyde bonding had created a material that was, pound for pound, stronger than the aluminum alloys of its era. "This," he said, "is where composite engineering began, not with space-age polymers or carbon fiber, but with wood and glue in furniture factories." One student raised her hand. "But sir, we don't build wooden aircraft anymore. Isn't this technology obsolete?" The professor smiled and walked to the window. Outside, a Boeing 727 was taking off from Logan Airport, its wings flexing visibly as it climbed. "Look at those wings," he said. "See how they flex? That's intentional." Modern aircraft are designed to absorb stress through flexibility, not rigid strength. We learned that from the Mosquito. And those wings, they contain fiberglass and resin composites, direct descendants of wartime wood lamination technology. He returned to the front of the classroom. In 1945, when the war ended, aircraft manufacturers abandoned wood construction. Too slow to compete with jets, they said. Too old-fashioned. For 20 years, everything was aluminum. Then, in the 1960s, we started hitting the limits of metal construction. Aircraft were becoming so heavy that they could barely lift their own structure. So we looked back at what the British had done with the Mosquito, and we asked, What if we applied these principles using modern materials? He picked up a sample of carbon fiber composite, black, woven, impossibly light. This is carbon fiber bonded with epoxy resin. Different materials, same philosophy. Layer materials with different grain directions. Bond them with adhesive stronger than the base material. Create a structure that flexes rather than cracks. The Mosquito's builders proved it could work. We just took their methods and ran with them. By the 1970s, composite materials were appearing in everything from racing cars to spacecraft. By the 1990s, the Boeing 777 was using composite materials for major structural components. By 2011, the Boeing 787 Dreamliner was more than 50% composite by weight, a direct lineage from a wooden bomber built in furniture factories. Today, Formula One cars use carbon fiber monocoques that function exactly like the Mosquito's laminated fuselage. Layers of material bonded with resin, designed to absorb impact through controlled delamination rather than catastrophic failure. Modern wind turbine blades use the same principles to create structures that are both impossibly light and incredibly strong. And in every case, the fundamental lesson is the same. Geoffrey de Havilland understood something in 1938 that the rest of the world took decades to learn. Strength isn't about using the hardest material. It's about using the right material in the right way. The final truth. The last flying Mosquito took its final flight in 1996, a Canadian-built aircraft that had survived 50 years after the war ended. As it climbed into British skies one last time, spectators on the ground heard that distinctive sound. Twin Merlin engines, not quite synchronized, creating a beat frequency that every wartime pilot remembered with affection. It landed gently, taxied to a stop, and shut down. The pilot climbed out and stood for a moment with his hand on the wooden fuselage, feeling the warmth of the engines, smelling that faint chemical sweetness that never quite faded. "Last flight," someone said. "Last flight for this one," the pilot corrected. "But the idea, that lives on." And he was right. The Mosquito's legacy isn't in museums or history books. It's in every composite aircraft that flies today. Every race car that uses carbon fiber. Every wind turbine blade that bends in the storm. Every engineer who asks not, "What's the strongest material?" but, "What's the smartest material?" The Germans who tore apart that captured Mosquito in 1943, who broke their chisels on British glue, who spent months trying to understand how furniture makers had out-engineered the Third Reich, they learned a lesson that transcends warfare. Innovation doesn't come from having the most resources or the most advanced technology. It comes from asking better questions. It comes from seeing abundance where others see scarcity. It comes from having the courage to solve old problems with new thinking. The British didn't set out to humiliate Germany. They set out to solve a practical problem. How do you build bombers when you don't have enough aluminum? The answer revolutionized aerospace engineering. The glue that held the Mosquito together wasn't just phenol formaldehyde. It was imagination bonded to necessity, compressed under the pressure of survival, and cured in the heat of war. And that's a formula no enemy could ever break. If you believe that true strength comes not from the hardest materials, but from the smartest thinking, leave a number 1 in the comments. If this story reminded you that innovation is born from constraints, not comfort, hit that subscribe button. And remember, the next time someone tells you that wood and glue can't change the world, show them the Mosquito. Because sometimes the most revolutionary idea is the one that everyone else called impossible. The museum that remembers the Royal Air Force Museum at Hendon sits on the northern edge of London, housed in hangars that once sheltered fighters during the Blitz. Inside, among Spitfires and Hurricanes and Lancasters, there's a Mosquito. It's not the most impressive aircraft in the collection, smaller than the bombers, less glamorous than the fighters. But visitors always stop in front of it, drawn by something that transcends mere history. The placard reads, "De Havilland Mosquito B Mank 16, wooden construction, maximum speed 408 mph. Combat missions 197, aircraft lost in combat 0. That last number tells the entire story. 0 losses. This particular aircraft flew almost 200 missions into enemy territory and came home every single time, held together by wood and glue and the absolute certainty of its design philosophy. An elderly man stands before it now, his hand resting on the velvet rope that keeps visitors from touching the fuselage. His name is Robert Clark, though everyone calls him Bobby, and he's 91 years old. He flew Mosquitoes during the war, including the Berlin raids that made Göring scream with fury. A young boy, maybe 10 years old, approaches with his father. "Is it really made of wood?" the boy asks. Bobby smiles. "Every bit. Birch plywood and balsa, glued together in furniture factories by people who'd been making dining tables and pianos the year before. But wood isn't strong," the boy protests. "Neither is metal, if you ask the wrong questions about it." Bobby gestures to the Mosquito's smooth lines. The men who built this understood something important. Strength isn't about being hard. It's about being smart. Metal is hard, so it cracks. Wood is flexible, so it bends and returns. When I got hit by flak over Hamburg, it punched holes straight through both wings. A metal aircraft would have torn apart. This one, he pats the fuselage gently. This one just absorbed it and kept flying. The father looks skeptical. "Surely modern aircraft are better, with aluminum and composite materials?" "Modern aircraft use composite materials," Bobby corrects. "Carbon fiber, fiberglass, advanced resins. And where do you think that technology came from? Right here. From furniture makers who learned that if you layer materials correctly and bond them with the right adhesive, you can create something stronger and lighter than traditional construction methods." He runs his hand along the wing's leading edge. Still smooth after 80 years. The varnish yellowed but intact. "I flew this exact aircraft," Bobby says quietly. W4072. She carried me to Berlin and back 9 times. To Hamburg, Copenhagen, Oslo, Munich, places where I shouldn't have survived. But every time she brought me home. His voice catches slightly. "All my friends who flew heavy bombers, so many of them didn't come back. The metal fortresses with their armor and guns, they were supposed to be safer. But we furniture makers in our wooden bombers, we had the highest survival rate of any bomber command squadron." The boy is staring at the aircraft with new respect. "It doesn't look scary." "No," Bobby agrees. "It looks elegant, beautiful even. And that's the lesson the Germans never learned. The most dangerous weapons don't announce themselves. They don't need to look intimidating. They just need to work." As Bobby turns to leave, he places his hand on the fuselage one last time. Through the varnish and the decades, he swears he can still smell it, that distinctive sweet chemical scent of phenolic resin, the smell that meant safety and speed and survival. In the museum gift shop, you can buy postcards of the Mosquito. The description on the back is admirably brief. The wooden bomber that terrorized the Third Reich and changed aviation forever. But that's not quite right. The Mosquito didn't change aviation through terror. It changed aviation by proving that the most advanced solution to a problem isn't always the most complex. Sometimes it's the most elegant. Epilogue. What the glue taught us. In a laboratory at MIT in 1965, aerospace engineering students gathered around a sample of laminated wood composite, studying its properties as part of a course on aircraft materials. The professor held up the British wartime adhesive sample and explained how phenol formaldehyde bonding had created a material that was, pound for pound, stronger than the aluminum alloys of its era. "This," he said, "is where composite engineering began, not with space-age polymers or carbon fiber, but with wood and glue in furniture factories." One student raised her hand. "But sir, we don't build wooden aircraft anymore. Isn't this technology obsolete?" The professor smiled and walked to the window. Outside, a Boeing 727 was taking off from Logan Airport, its wings flexing visibly as it climbed. "Look at those wings," he said. "See how they flex? That's intentional. Modern aircraft are designed to absorb stress through flexibility, not rigid strength. We learned that from the Mosquito. And those wings, they contain fiberglass and resin composites, direct descendants of wartime wood lamination technology." He returned to the front of the classroom. In 1945, when the war ended, aircraft manufacturers abandoned wood construction. Too slow to compete with jets, they said. Too old-fashioned. For 20 years, everything was aluminum. Then, in the 1960s, we started hitting the limits of metal construction. Aircraft were becoming so heavy that they could barely lift their own structure. So we looked back at what the British had done with the Mosquito, and we asked, what if we applied these principles using modern materials? He picked up a sample of carbon fiber composite, black, woven, impossibly light. This is carbon fiber bonded with epoxy resin. Different materials, same philosophy. Layer materials with different grain directions. Bond them with adhesive stronger than the base material. Create a structure that flexes rather than cracks. The Mosquito's builders proved it could work. We just took their methods and ran with them. By the 1970s, composite materials were appearing in everything from racing cars to spacecraft. By the 1990s, the Boeing 777 was using composite materials for major structural components. By 2011, the Boeing 787 Dreamliner was more than 50% composite by weight, a direct lineage from a wooden bomber built in furniture factories. Today, Formula One cars use carbon fiber monocoques that function exactly like the Mosquito's laminated fuselage. Layers of material bonded with resin, designed to absorb impact through controlled delamination rather than catastrophic failure. Modern wind turbine blades use the same principles to create structures that are both impossibly light and incredibly strong. And in every case, the fundamental lesson is the same. Geoffrey de Havilland understood something in 1938 that the rest of the world took decades to learn. Strength isn't about using the hardest material. It's about using the right material in the right way. The final truth. The last flying Mosquito took its final flight in 1996, a Canadian-built aircraft that had survived 50 years after the war ended. As it climbed into British skies one last time, spectators on the ground heard that distinctive sound. Twin Merlin engines, not quite synchronized, creating a beat frequency that every wartime pilot remembered with affection. It landed gently, taxied to a stop, and shut down. The pilot climbed out and stood for a moment with his hand on the wooden fuselage, feeling the warmth of the engines, smelling that faint chemical sweetness that never quite faded. "Last flight," someone said. "Last flight for this one," the pilot corrected. "But the idea, that lives on." And he was right. The Mosquito's legacy isn't in museums or history books. It's in every composite aircraft that flies today. Every race car that uses carbon fiber. Every wind turbine blade that bends in the storm. Every engineer who asks not, "What's the strongest material?" but, "What's the smartest material?" The Germans who tore apart that captured Mosquito in 1943, who broke their chisels on British glue, who spent months trying to understand how furniture makers had out-engineered the Third Reich, they learned a lesson that transcends warfare. Innovation doesn't come from having the most resources or the most advanced technology. It comes from asking better questions. It comes from seeing abundance where others see scarcity. It comes from having the courage to solve old problems with new thinking. The British didn't set out to humiliate Germany. They set out to solve a practical problem. How do you build bombers when you don't have enough aluminum? The answer revolutionized aerospace engineering. The glue that held the Mosquito together wasn't just phenol formaldehyde. It was imagination bonded to necessity, compressed under the pressure of survival, and cured in the heat of war. And that's a formula no enemy could ever break. If you believe that true strength comes not from the hardest materials, but from the smartest thinking, leave a number 1 in the comments. If this story reminded you that innovation is born from constraints, not comfort, hit that subscribe button. And remember, the next time someone tells you that wood and glue can't change the world, show them the Mosquito. Because sometimes the most revolutionary idea is the one that everyone else called impossible.